So let's learn how to compute now frequency distribution. So instead of just computing one particular frequency for one particular interval, we will make a set of frequencies. We will compute a set of frequencies. So the idea is following. We would like to compute frequencies for different intervals of the values range. To do that, first of all, we need to take the whole range. So in our case, we take the smallest value and the largest value and get the range a little bit wider. So the smallest and the largest value are all inside this range, inside this interval. So in my case, I set the boundaries of my big interval of the big range as 8.8 and 10.8. So both smallest and largest values are inside, right? Now I need to take this range and split it into equal sub-intervals, into equal beans. So this is how it looks like. In my case, I use 5 different beans, and then you can see that they are equally distanced. The boundaries are equally distanced, right? So we split our values range into equal portions, into equal intervals. So this is the intervals. And now what we need to do, we need to repeat the procedures that we learned in the previous video. We simply count how many values we have within each bean. For example, if we take a bean between 8.8 and 9.2, apparently we have only one value, so we just write 1 here. Between 9.2 and 9.6, we have 2 values, right? And then between 9.6 and 10, we have 3 values, and so on and so forth. Here you can see that sometimes the values, especially if we use a small number of decimals, the values can lie exactly on the boundary of the bean, right? So for example, in this case, you can see for this bean, we have boundaries as 10 and 10.4, and then we have one particular value which is exactly which lies on the boundary, on the right boundary. So the rule is very simple. The left boundary is the left boundary is not included, the right boundary is included. So it means that, for example, 10.4 will be counted in this interval, not in this one. Okay, so that's just a simple rule. So in this case, this is why we have 3 here, and this is also why we have 2 here, because 9.6, you can see 9.6, we kind of it's included because it's on the right boundary. It's included to this interval, but if it were in the left boundary, it's not included. So now we can make a frequency distribution table. So for every interval, for every bean, sometimes we'll call it bean. For every bean, we have a count or a frequency, how many values we have in each bean. Of course, frequency, it's absolute values. It depends on the sample size, but we can normalize the frequencies. And in this case, we simply take a count, take a frequency, and divide to the total sample size, so the total number of values. That gives us a relative frequency, so we know the percentage. For example, here we have 10% of the values, 20% of the values, 30, 30, and 10. Okay. Now we can also visualize this. And for visualization, it doesn't matter if you use the real frequency or relative frequency, the shape of this plot will be the same. And visualization is very simple. You make a bar plot. The width of every bar, it's the same as the width of the interval of the bean. And the height of the bar, in this case, it's the same as the frequencies. So that's why it's called frequency distribution histogram. It shows you how frequencies are distributed within this range of the values. And that gives you a very important information about your data. It tells you where most of the values are, where is the most dense part of your interval. And most of the time, you will see what is called a central tendency. So the values tend to be crowded in the center of your range. So in this case, you can clearly see the central tendency here. So most of the values lie within this range, which is almost in the center of the interval, right? The frequency distribution table actually has a direct relation to quantiles, to what we have discussed before. You simply need to accumulate frequencies. Look, so this is the quantiles, the percentage that we calculated for every interval, and this is the relative frequencies, right? This is the relative frequencies. Now you can see that, for example, this one is what it means, right? So remember, the quantile means that, or the percentile in this case, means that 60% of the values are smaller than 10, because 10 is the right boundary of this interval, right? So this is 10. So we can say that 60% of the values are smaller than 10. But on the other hand, how we can compute it? We need to take the relative frequencies all up to this, and then simply sum up them, right? So we kind of accumulate relative frequencies in order to compute quantiles, in order to compute percentiles. So this is the relationship. So frequency, it tells you the percentage of values you have within each interval, while the percentile or quantile, it tells you how many values you have up to this interval, right? So it's a kind of accumulated value. And that's why we will call this as a cumulative relative frequency. So instead of percentile or quantile, we will call it cumulative relative frequency. Now let me summarize what we have learned so far. So we learned that we can describe our measurements using different statistics and plots. First of all, the simplest plot you can make, it's a strip chart. It simply shows you a value along one axis, x-axis, and the position of the value corresponds to the value itself. You can also compute rank-based statistics. So you order your values, compute rank for every value, and then you can compute statistics based on these ranks. And we know that there are 5 main statistics. It's the smallest, it's the largest value, it's the median, and also 2 quartiles, the Q1 and Q3. You can visualize these statistics using box and whiskers plot. So every part of this plot corresponds to one of these 5 statistics, right? We also know that we can also detect outliers and show outliers separately. We can make percentiles plot by computing the percentage of values to be expected smaller than given. We can have 2 representations, so we have x and p, the values and the percentage, and then we can use these 2 representations to make the percentiles plot. Now we also learn how to compute frequency distribution table and how to visualize it by showing frequency distribution histogram. So this is what we have learned so far. Now let's talk a little bit more about this distribution histogram. First of all, I split all my values into 5 different intervals, into 5 bins. But what happens if I use more or if I use less bins? So in this case, you can see this is the values that I got. I use 5 bins and 10 values. It's my sample, the original sample. What if I use, for example, 4 bins? So in this case, you can see that the shape is a little bit different, right? So here we kind of have a skewed, so we have a longer left tail than the right tail. Here we have other way around, right? So this is the shorter and this is a little bit longer. What if I use more bins, for example, 8 bins? In this case, you can see that the plot looks very, very strange. And why it looks strange? It's simple. Because we don't have enough data to accumulate frequencies inside each bin, right? So you remember that we have only 10 values, and when you have 8 bins, it means that you need to count values within each bin, but we have only 10 values, so it means that we will have either 1 or 0, or in this case 3, so we don't have enough values to accumulate this. If your sample size is larger, for example, say sample size is 100, then it's not a problem. So in this case, you can see that I have a sample size of 100, so I have 100 of apples, sugar content of hundreds of apples. And then by varying the number of beans, I don't change the shape much. Of course, I have a little bit more details here, a little bit less details here, but in general, you can see that the shape is the same. So what it means? It means that although the frequency distribution histogram is an important tool, it can show you additional information about your sample. Using it for a small sample size, if your sample size, let's say below 30, it should be done with caution, because sometimes it can show you some strange patterns, and without experience, it will be difficult to assess it. Now we can summarize that distribution of frequency, so frequency distribution histogram, it's a very important tool that provides you additional information about your data. And first of all, it provides you a shape of your data, where you have where you expect to have the value more often, where you expect to have the value less often, and so on and so forth. So it kind of shows you a density of the values within the whole range. However, it's unstable and ambiguous for small n. So if you have a small sample size like 10 or 5, then distribution histogram is not the best plot to use. So you can use other plots, which we will also learn later in this block number 1. But it's very important to understand parametric approach. So we will continue discussing the distribution histogram in the next video, because it gives us a bridge between non-parametric and parametric approach. So this is what you need to know about distribution of frequencies. And in the next video, we will take one step further and talk about how to turn frequencies to densities.